So now we're going to look at normal operators, which are a slight generalization of self-adjoint operators. A normal operator is one that commutes with its adjoint. So TT star and T star T are the same. So if you've seen commutator bracket in 306, then this is saying that the bracket of T and T star is equal to 0. Okay, so first just an example. If we go back to looking at the one that we talked about before on R2, rotation by pi over 2. So clockwise rotation by pi over 2 is normal, but not self-adjoint. And so to see that, let's see. Well, if we look at T x1 x2, and we'll use the dot product as our inner product, so against y1 y2, then rotation by pi over 2 is minus x2 x1, and so that's dotted with y1 y2. And so working out the dot product there, let's see, we have x1 y2 minus x2 y1. And so I just wrote it that way so that you can clearly see the x1 part and the x2 part, so that it's easy to rewrite this as x1 x2 dotted with, and then what must it be? Well, x1 got a y2 next to it, and x2 got a minus y1 next to it. So then that tells you that T star of y is y2 minus y1. All right, and so this one is rotation by minus pi over 2. And, I mean, if you look at it, it's also the negative, like this is minus the positive rotation, right? So that should be clear. Okay, and so then we have that T is not equal to T star, because one's rotating one way, the other's rotating the other way. But TT star and T star T are both equal to the identity, because T star is actually equal to T inverse. So this is a special thing. When the inverse is equal, when the adjoint is equal to the inverse, this is called a unitary operator. And unitary operators play a special role. Basically, if an operator is unitary, you should think of it like some sort of rotation in high dimensions. In particular, it fixes the length of all vectors. So their lengths stay the same, they just rotate in various directions. And that's sort of related to the next result that we're going to see here in a moment. And by the way, remember the fact that this is not self-adjoint, but that it is normal. This has to do with the fact that T has no real eigenvectors, and that TVV is equal to 0 everywhere, but T is not the 0 map. So these properties are related to each other. Okay, so for a quick little pickup result about normal operators, we have that an operator is normal, normal is normal if and only if it preserves the norm. for all vectors. Okay. The condition of unitary, by the way, is equivalent to saying that it preserves the inner product for all vectors, which is a stronger condition. So let's see. If we assume that, and this is going to be, we're going to do both directions simultaneously here of the if and only if. So if we start off with t star t minus tt star being equal to 0, this is true if and only if t star t minus tt star applied to v against v in the inner product is equal to 0 for all elements of v, and that's by 7.16. Okay, so then doing a little bit of arithmetic here, I can use linearity in the first slot to split this, and so this is t star t v against v minus tt star v against v being equal to 0, or in other words, being equal to each other for all v and v. And then I can just move t's around. So in the first one, if I shifted t star over to becoming a t, then I have tv, tv. And in the other one, if I put the t over, it becomes a t star, so I have t star v, t star v. And then taking square roots of both sides of this equation is equivalent to what was given in the statement of the theorem. And we're done.